Okay. Please. Okay. So first, I would like to thank Alfredo and the other organizers to invite me here. 20 years ago, I was a PhD student of Alfredo, and I indeed was in this area. Then I changed, and it is a pleasure to come back here and talk in this conference. Okay. So first, I would like to introduce my collaborators in this work. This is my PhD student. This is Diego here from University of Buenos Aires, Augusto Roncaglia for UBA in Buenos Aires, and Lucas Sellery in the Federal University of Goiás, and Norton de Almeida also for the Federal University of Goiás. I'm talking about here about the work probability distribution, and this is a concept that is important in quantum thermodynamics, and the goal of this talk is to show which is the structure of the work probability distribution in system with large Hilbert spaces, and how we can take advantage of this structure to, with random models, to describe this work probability distribution function in quantum system with large Hilbert spaces, as for example, many-body system. So the outline of this talk is, first I will brief review the fluctuation relations in classical and quantum non-equilibrium thermodynamics. Thus, I will talk about the celebrated Jasinski relation. Then I will talk about how to introduce a probability distribution function in quantum mechanics through the two-energy measurement protocols that allows to extend this classical relation in quantum mechanics. Then I will talk a little bit about random models to describe the statistical properties in many-body interactive systems, a little bit about integrability and chaos, and then I will talk about our approach, how we can use these random models to describe the probability distribution function of work in many-body interactive systems. And I will compare this approach with a realistic system of a change of a spinum 1/2 system. Okay. And also I will talk about how is the structure of the probability distribution of work if you use the classical Gaussian ensembles. Okay. So let's start showing which is the famous Jasinski relation in classical mechanics. If you start with a thermal distribution in the phase space, so the trajectories are here, distributed with this thermal distribution, and your Hamiltonian depends on a parameter, and if you change this parameter, the trajectories evolve, and you have a final distribution here. So the work that is in classical mechanics just the difference of the value of the Hamiltonian in the initial value of the trajectory and the final value of the trajectory is because you have a distribution, is a stochastic variable, and if you calculate the probability of this stochastic variable, it's easy to show this relation here, that is the average of this exponential, where this beta here is the inverse temperature, and this delta F here is the difference of free energy at equilibrium. But the interesting thing of this relation here is that the final state here is way out of equilibrium. Okay? So this relation has a remarkable result that for all closed but arbitrary strongly non-equilibrium processes, the average exponential work is determined entirely by the equilibrium parameters contained in the difference of free energies at equilibrium. Okay? So if you want to extend this relation in quantum mechanics, first you have to know which is the definition of work, okay, in quantum mechanics. So let's start, for example, with a Hamiltonian at time 0, and you have the eigenvalues of this Hamiltonian, and you applied a process, a unitary process. It could be an external field controlled by some parameters, and you end up with a final Hamiltonian. This is, and one definition of work could be just the difference between these eigenenergies. So if you start with a general initial state, a general non-analogous state of the initial Hamiltonian, the energy is not well defined in this state. So in general, this is an stochastic variable also in quantum mechanics. Okay? Clearly, this stochastic variable cannot be the eigenvalues of any Hermitian operator, because you have much more numbers here than the dimension of the Hilbert space that you are working. So it's not, but the crucial step in order to verify a relation that, like the Jarzynski relation, is to get information of the system of this variable through a process of two energy measurements. Okay? So if you get information of the system through a protocol of two energy measurements, then you get a probability distribution of this variable work that indeed verify the Jarzynski relation. So the corresponding work distribution is known as two-point measure distribution. Which is this distribution? Well, if you perform two energy measurements, you have to sum up all the alternatives. Here you have the joint probability distribution associated with this process of two energy measurements. First, you have the probability to obtain the eigenenergy, the first eigenenergy in the first measurement after a projective measurement in the initial state, and this is the probability to obtain the second eigenenergy after having measurement the first one. Okay, you sum all the alternatives, and this is the probability distribution of the variable that you call work. Okay. In a unitary process, this is the probability for the second measurement, And if you start with a thermal state, that is the requirement to verify the Jarzynski relation, the first measurement is superfluous, because you already have the probability distribution of the population of the initial state that depends on this energy. Okay? We are interested in processes that are called quench, where are processed too far, when you can approximate the unitary operator just with the identity. So in that case, this probability of work reduced to this expression here. And you can rewrite this expression here, just ordering this sum here in this way. So here you have the so-called strength function, also known as the local density of states. So the probability distribution is just the sum of this Boltzmann factor here, multiplying by the strength function. Okay? This strength function is characterized in general by a centroid that is calculated in this way, and a variance when it exists. Maybe the function that can here don't have up. In a moment, it's become more clear what I'm saying. Okay, but the variance is calculated here in this way, and the important thing is that these matrix elements are matrix elements of the final Hamiltonian in the unperturbed Hamiltonian that is the initial Hamiltonian. So you can calculate these values without diagonalizing the final Hamiltonian. So for large hero spaces, for example, in many body systems, yesterday we learned in the Klaus Richter talk that you can do some smoothing in energy. So you substitute this sum by integrals, where you define some in the Klaus talk about this as the mean level density, and you can rewrite so this expression for the work probability distribution in this way, okay? With this, in this way, where you define also an energy cost graining strength function in this way, okay? So the expression that for large hero spaces, for example, for many body systems, the expression for the work probability distribution that verifies the Jarzynski relation is this one. When you have an energy level density, smooth level density, energy constraining level density, and an energy constraining strength function. These are the two ingredients that you need in order to describe the probability distribution of work. So the question is, how do you get this expression in general? If you use the energy comps for the level density, you recover the exact expression. This is okay. So, but the advantage of this expression here is that in order to describe this probability distribution, you don't need to know exactly the eigenvalues and eigenvectors of the initial and final Hamiltonian in order to describe these smooth functions here. But the question is there any generic description of this smooth function in many body interacting systems? This is a question that, for example, in the talk of class, we learn a little bit about how to get this spread for the level density generic curves in many body systems. Okay, so we have this expression, and now we want to learn if random models can help us to describe this distribution here. Okay, so we imagine that in a system of large Hilbert spaces, this energy smoothing describes some smooth curve where the real probability distribution of work oscillates a little bit around this smooth curve. Okay, so how it works for random models to describe this probability distribution? Well, imagine that you have a generic random model that describes the initial and the final Hamiltonian. So you have showing probability distribution for the eigenvectors and eigenenergies that here are the vectors of eigenenergies, and these theta here are vectors that enclose all the parameters that describe the eigenvectors. Okay, and I am not assuming nothing about the random models, could be anything. Okay, but I want to show which is the approximations and the characteristics, the general characteristics that the random model have to have in order to describe ensembled average of the work probability distribution, that is the exact work probability distribution that is here, that has the structure given in this expression here. Okay? So we perform the average of this expression here, and first the statistical equivalence of any eigenenergies and eigenvectors gives this expression here with this n square comes from this double sum here. And then we can do what is called the annealing approximation, that is just to split the average in the numerator and in the denominator. Okay, this is well known in the literature as an annealing approximation, and for expressions that are very similar to the work probability distribution, this kind of approximation is proven that is very accurate in the limit of n, that is the dimension of the Hilbert space, great, and for every value of the inverse temperature. Okay? So if you impose that your ensemble, that is in principle generic, has the property that there is a statistical independence of eigenvectors and eigenenergies, this joint probability distribution is just the product, and it's very easy to see that this expression here can be written in this way here, okay, where you have the mean level density of initial random spectrum here, and also the strength function of the random model, that is the average of the through the probability distribution of eigenvectors here. Okay, so you end up with an expression that for the ensemble average that has the same structure here of this expression here. Okay. Well, well, two approximations were done here. One is the annealing approximation, and the other is the requirement that statistical independence of eigenenergies and eigenvectors, but nothing else. Okay. In order to this expression has a utility, you need to have some ergodic property where the mean is the running average, that is the expression that you get from a single drum of Hamiltonians from the ensemble, is very close to the mean that is here. Okay. And this the verification of this ergodic property for Gaussian ensembles, the traditional Gaussian ensembles, were done in this work here. That's what was published last year. So how it works? The mean level density is in the limit of large dimension is just the semicircle law for these Gaussian ensembles here, the GOE and the symplectic ensemble. This semicircle law is characterized by the average level spacing and the center of the spectrum, that is this number here. So the strength function is just proportional to the mean level density of the final spectrum, and the expression for Gaussian classical Gaussian ensemble that we get is this one, that is just a convolution smoothed by the Boltzmann factor. Okay? So this is the thermal average of the convolution of two semicircular law corresponding to the level density of two random spectra. This world probability distribution is characterized by only by the average level spacing and the center of each of the spectrums. Okay? So we verified the ergodic property for this expression. Here we have some plots. For example, we define the number of effective energy levels that contribute to this expression here, that is defined as with this number here. This is the inverse temperature, and this is the average level density, level spacing. So for high temperature, where this number over n is much greater than 1, we have this result for the black curve here is just this expression here, and the other is just the Ramanan average when with the exact expression for the world probability distribution. Okay? So you see that the oscillations are very narrow. Okay? For beta going to 0 is just the convolution, okay, of two semicircular law. For intermediate temperatures, we have also a very good result, okay. And for high temperatures, here we show that if you choose n not so great, the oscillations are greater. But if you increase the dimension, we go for 300 up to 5,000, you see that the oscillation, with fixing the temperature, okay, in this calculation the temperature is fixed, only we increase the dimension of the space, you see that the oscillations are narrower, okay? Well, but nowadays we know that the fluctuation properties of classical random matrices are generic, and therefore applicable for local spectral statistics of a wide variety of quantum systems with few degrees of freedom, with a classical counterpart in the regime of fully chaotic dynamics. For example, we know that the level spacing distribution is well represented by the bigness of mice and is a good approximation for in real system with but all other results are not good. For example, the semicircle law for the level density not describe any physical system, and here the crucial point in order to have a good description of some properties of your system is we have to have few degrees of freedom, a classical counterpart, and a fully chaotic dynamics. Okay, and in many-body interactive system, you don't have a few degrees of freedom. It's clear how to obtain a classical counterpart in many systems, and also is not. We learned also in the Klaus Richter talk yesterday that is controversial how to define chaotic dynamics in this kind of system. But it is clear that in order to describe some statistical properties in many body systems, you need some different ensembles, and this new description have a new definition of how to consider a system integrable or chaotic that is not only linked with the properties of fluctuations in the energy spectrum, but is linked also with the characteristic of the structure of eigenstates. Okay? So the many bodies random models that we are using in this work here are characterized by Hamiltonian that can be split in two parts. One part describes the non-interacting constituent of particles or quasi-particles. This can be considered in general in these random models as a diagonal Hamiltonian with or without diagonal random entries. Is known as mean field Hamiltonian. This is because it comes from the mean field approximation that defines the single particle states that are filled with a number of non-interacting particles. And you have an all the interaction of the system are embedded here in this part of the Hamiltonian. And this is this part here have interactions with rank k, where k is the number of single particle states that are connected by the interaction. This type of random models are known as 1 plus k random models. And when k is equal to 2, you have the known two-body random ensembles or embedded random ensembles. The nature of this structure, where this part here has random entries, but with the constraint of k rank of interactions, impose in the case of two-body nature of the typical interaction to important restrictions, such as the band-like structure of the Hamiltonian and the presence of non-vanishing and repeated matrix elements. In the case where you preserve this structure, band structure of the Hamiltonian, but you use for the for individual entries random Gaussian distribution, These type of random models are known as embedded Gaussian random models, okay? And there are a lot of results that some of them I'm going to show here. So here I will present how to use random models and our approach in order to describe the work probability distribution in realistic systems, many body system. This is an example that we take from this paper here, where we use two models. The first one is the XXZ Hamiltonian, defined in this way here, that is integral for any value of mu here. That is the strength of the perturbation of this Hamiltonian here. Is a first neighbor interaction Hamiltonian, and the levels spacing distribution is Poissonian. Also, the Brody parameter can be associated with integral dynamics. The second model is this one here, where H1 is just this Hamiltonian here, and we have a perturbation given by this expression here. In this case, you have second neighbor interaction, and this has a chaotic regime that could be characterized by the mean level spacing nearest neighbor spacing distribution with the bigness or mice, and you have a transition from integral to chaotic for some value of the parameter lambda. Okay? So, sorry. So we want to see if this expression here are, in principle, if they are equal or not, okay? And if they are equal, if it describes well the exact probability of work in this kind of system, okay? Well, in this paper here was shown that indeed the smooth, the energy constraint mean level density is equal to the ensemble average level density that comes from embedded Gaussian ensembles. And here you see that the black curve is the level density that is Gaussian in all cases, and is a result for embedded Gaussian ensembles. And this is the histogram is just the smoothed level density. And the characteristic is that in both regimes, in the integral case and in the chaotic case, the level density is Gaussian. Also, in this paper here, it was shown that the energy smooth strength function is almost equal to the energy average strength function that comes also for the embedded two-body Gaussian ensembles. So now we want to see, so it's equal to use the energy constraining or the ensemble average that comes from the two-body Gaussian ensembles, and we want to see if this expression here well describe the exact formula for the work probability distribution in quenchs. Okay, so here we start with a strong interaction, and you see that we go from chaotic to chaotic, but because the interaction is strong, the strength function is Gaussian, okay, and the level density are Gaussians, And this is the comparison between this expression here and this one, okay? And you see that are a rather good and a small fluctuation around the black curve. For intermediate temperature, we have also a very good agreement. And for low temperatures, it fails. And the explanation is very easy, because in low temperatures, we are exploring only the tails of the level density, and we know that the tails of the exact level density and the result from the Gaussian expression from the embedded Gaussian ensembles are not good, okay? So for low interaction strange that goes from chaotic to also to chaotic, but now the strength function is a Lorentzian. For high temperatures, we have a very good agreement, and the oscillations are about the ensemble average is small. For intermediate temperature, also we have a very good agreement, but for low temperature also fails for the same reason. Okay, I'm finishing now. So for low interaction strength, we go from integrable to integrable. Okay, in this case, also the level density here is Gaussian, but the strength function here are Lorentzian, Breit-Wigner form, and we have very good agreement also for high temperatures, for intermediate temperatures, but it fails for low temperatures. So we have here the conclusion. We have shown the structure of work probability distribution for quenchs in systems with large Hilbert spaces. The essential ingredients are the energy cost gradient density of states and the energy cost gradient strength function. We show in many body quantum interacting system, which is the general property that a random model has to have in order that the ensemble average work probability distribution has the structure of the energy cost gradient probability distribution. And we compare in a realistic two-body interacting spin one-half system our approach. So thank you very much for your attention. And here are the group of quantum information in Rio de Janeiro, where I belong. Okay.
Concerning the work function and the strength function, I was wondering if you could calculate them in a semi-classical manner, that is using different Fleck